So far, you have learned to write formulas for molecules and for ionic compounds. Now we're going to get into another whole realm of chemistry, which takes us from molecules to chemical reactions. So obviously you're going to have to use molecules, but we're going to go a lot further than we've gone before. Now, before we get started on this, I want to take you back to something you learned in Unit 2 when we were talking about energy. You learned that energy can neither be created nor destroyed in a chemical or physical process. We're going to take that same law of conservation, and this time, instead of talking about energy, we're going to talk about matter. Because as it turns out, matter also cannot be created or destroyed in a chemical or physical process. Now at this point, hopefully you understand that all matter is made out of atoms, so we can take that a step further and say, all right, now we know that atoms cannot be created or destroyed in any chemical or physical process. Well then, what can happen in a chemical reaction? Well, the atoms themselves are not going to change much, but their associations are going to change. So if one atom maybe is bonded to another atom, in a chemical reaction, that might break apart. And we might form new bonds. They can be ionic bonds where we have to transfer electrons, or they can be covalent bonds where they're sharing electrons, but we can make new bonds and we can break old bonds. And after we break the old ones, we can kind of move the atoms around and get them near other atoms that they weren't near before, and then make the new bonds. So we get new substances with new properties. So that's the cool thing about chemical reactions. We take one kind of matter and transform it into a totally different kind of matter, but it's all made of the same atoms. The building blocks are the same. We cannot create them, we cannot destroy them, we can just shift them around. And when we shift them around, that gives the matter itself, on the macroscopic scale, very different properties than it had before. So thinking again about that law of conservation of matter, when we write a chemical equation, we have to represent this conservation of atoms. We have to show the chemical reaction in a way that demonstrates that we do not create atoms and we do not destroy atoms, we just move them around. Which means that we have to look at what's on the left side of the equation and what's on the right side of the equation and make sure we have the same number of each type of atom on both sides. So let's begin. And I'm going to start with that is hydrogen peroxide, H2O2. Now hydrogen peroxide is the stuff in that brown bottle, probably under your bathroom sink or in your medicine cabinet or something like that. And I remember when I was growing up, my mother liked to make me soak my fingers in it if I had cuts. It was supposed to disinfect them, which it does. It does disinfect them, and it doesn't sting very much. So it was a great step up from that iodine stuff that was dissolved in alcohol and really stings a lot. So hydrogen peroxide, though, is kept in a brown bottle because it will break down. It will decompose. And when it decomposes, it does this. It breaks down to water and oxygen. So you can see that hydrogen peroxide, which is toxic, that's why it's a good disinfectant, because it will kill the bacterial cells. It will also, by the way, kill your cells. So you don't want a whole lot of it, and you wouldn't want to drink it or anything, but it will at least kill the bacteria in the vicinity of that little cut that you get on your finger. And since those cells have already been damaged, it's okay if a few more die. As a matter of fact, your cells make hydrogen peroxide all the time. It's a byproduct of your metabolism. And so you have an enzyme in your cells called catalase, which catalyzes this reaction and causes the hydrogen peroxide to break down into water and oxygen. And that's really important, because if you didn't have that enzyme, then your cells would make this hydrogen peroxide and they would just poison themselves. So back to business here. We're starting off with a molecule that's got 2 hydrogens and 2 oxygens in it. So we want to make sure that when we write a chemical reaction, we can show that we haven't created any molecules or any atoms, and we haven't destroyed any atoms. We definitely will create and destroy molecules, but the atoms have to be the same. So let's look at what we've got up here and kind of take an inventory. And we can say from here, I can tell that I've got 2 atoms of hydrogen. And from here, I can tell that I've got 2 atoms of oxygen. Now let's take inventory on the other side of the arrow. Think about the arrow as a transformative process. And what we've got over here is before. And what we've got over here is after. So before the reaction, this does not exist, and we only have this. After the reaction, this does not exist, and we only have this. So we want to make sure that we've got the same atoms, that none of them escaped, and that we didn't somehow create new ones. Right here, that tells me that I again have 2 hydrogens. So that looks pretty good for hydrogen. But oxygen occurs in 2 places, here and here. And since there's no subscript here, that tells me there's 1 atom of oxygen. And there's a 2 here, which tells me there's 2 atoms of oxygen. So altogether, I have 3 atoms of oxygen. Now that is a problem, because now I am violating the law of conservation of matter. Over here there's 2 oxygens, and over here there's 3 oxygens. That means somehow I gained an oxygen, and that can't really happen. So what I'm going to do is use something that we call coefficients. Coefficients are large numbers that we place before the molecule. These are called subscripts. A coefficient will not be a small number like this, it will be a large number, and it will go before, and it will tell me how many molecules I have. So I'm going to need to rewrite this since I've made it all messy. I'm going to rewrite it in black. Alright, so I need to use coefficients to make sure that I have the same number of atoms on both sides of the equation. So what I'm going to do is say to myself, well, I need to get this oxygen straightened out. I need more oxygen on this side. So how about if I put a 2 here? Now you might say to yourself, well, wouldn't it just be simpler to change that 2 to a 3? No, that is not allowed. You can't go messing with the subscripts, because hydrogen peroxide is a molecule that looks like this. It has a hydrogen connected to an oxygen, connected to another oxygen, connected to a hydrogen, and that's what that molecule looks like. And it only has 2 oxygens in it, and I can't go sticking another oxygen in there because that's not what that molecule looks like. So you cannot change the subscripts, but I can decide to have 2 molecules. So what I've represented up here right now is really this, H-O-O-H. So here's 1 molecule, here's another molecule, and that's what that 2 means. I now have 2 molecules. So if you add this all up, you can see that you've got 4 hydrogens and 4 oxygens. So let's go back to my black here, and we'll make that 4. And you might think that's not really getting you anywhere, but it kind of is, because I know I need more oxygen, and so the best thing I can do is get more oxygen by taking 2 of these molecules. Now what happens? Well, first of all, I messed up my hydrogens, didn't I? So I'm going to have to put a 2 over here as well, because when I do that, now I have 4 hydrogens here and 4 hydrogens here, and that magically solved my problem, because I have 4 oxygens over here, 1, 2, 3, 4, and now look what I have over here. I have 2 water molecules, and I'll go ahead and draw that out so you can see how that works. So here's a water molecule, H-O-H, and the fact that I had to write a 2 there says that I've got 2 molecules of water. This is an oxygen molecule that's made up of 2 atoms. So there we go, there's our 2 oxygens connected together. There is no coefficient there, at least not yet. So right now that tells me I only have 1 of those molecules. So let's see what I've got here. So over here I've got 1, 2, 3, 4 hydrogens. Over here I've got 1, 2, 3, 4 hydrogens. Over here I've got 1, 2, 3, 4 oxygens. And over here I've got 1, 2, 3, 4 oxygens. So yay! Now if you weren't going to draw pictures and you were just going to keep track of this by something like this, we'd go back up here and say, well, 2 times 2 is 4. So I've got 4 hydrogens. And then I've got 2 oxygens here. 2 times 1 is 2. Plus another 2 over here. So 4. And now you can easily see that we have the same number of atoms on both sides of the equation. Now this looks a little bit trial and error, and it looks like it will be really hard. And it is trial and error, and I think at first it might be kind of hard, but after a while you'll kind of get the hang of it, and you'll be able to see how to do things. And it's not necessary to do this tabulating unless you want to. Some people find it's helpful, especially at the beginning, but after a while you won't do that anymore. You'll just be able to keep track of it in your head. So let's try a couple more examples. Let's take sodium. Sodium is a really soft metal. It's kind of gray colored and it's about the consistency of cheese. You don't think of metals that way normally, but sodium is a very soft metal. It's also very, very reactive. You'll never ever see this in nature because the minute it gets near oxygen or water, it reacts violently. So you never find it in nature, but you do find it in my chemical storeroom in little bottles stored under oil so it doesn't get near any oxygen or water. But let's say it does get near some water. My chemistry teacher in high school used to tell us a story about this reaction. He said that when he was in college, now I don't know, I really wonder sometimes some of the stories he told us if they were actually true because they were wild. But supposedly he and some of his buddies got into the chemical storeroom in college and stole a pound of sodium. And they took it down to the river and they threw it in. And it made a huge explosion. All right, anyway, let's see what happens with this. You're going to make sodium hydroxide and hydrogen gas. So if we know that, then we have a chemical equation which isn't balanced, but now we're going to have to balance it. So what do we have over on this side? Looks like I have 1 sodium, and I have 2 hydrogens, and I have 1 oxygen. All right, I know I have 2 hydrogens because this little 2 tells me that there's 2 hydrogen atoms in every molecule of water. That little 1, which is invisible, tells me that I have only 1 atom of oxygen. All right, let's go to the other side, and I have 1 sodium, so far so good. I have 1 oxygen, all right, so far so good. And how many hydrogens do I have? Well, 1 here and 2 more here gives me 3 hydrogens. All right, so it looks like I need some more hydrogens over here because I only have 2 over here, but I have 3 over here. So if I'm going to get more hydrogens, the only thing I can do really is to put a 2 here. Now, it doesn't have to be a 2, it could be 3 or 4, but let's start with a 2 and see what happens. So if I do that though, I have messed up my oxygens, haven't I? So if I want to keep track of things here, we'll call that a 4 now, and we'll call that a 2 now. So I've messed up my oxygens, and now I have 2 of them, so that means I'm going to need 2 on the other side. So let's put a 2 here. So that's nice. That gives me the 2 oxygens I need. It also doubles the number of sodiums. And now I'm up to 4 hydrogens. So let's see if I can go back to the other side and make this work out. So the 2 oxygens, that looks pretty good. The 4 hydrogens, that looks pretty good. But I only have 1 sodium over here. But that's a pretty easy fix because I can go up here and put a 2. And now I have 2 sodiums. So let's just do a sanity check here. 2 sodiums, 2 sodiums. 2 times 2 is 4 hydrogens. 2 hydrogens plus 2 hydrogens is 4 hydrogens. 2 oxygens, 2 oxygens. Yes, so that worked. So hopefully you can see what's happening here, that this 2 goes with everything in front of it. So for example, over here, this 2 tells me I have 2 sodiums, 2 oxygens, 2 hydrogens. Where these little subscripts only go with the atom that they're right next to. So this 2 goes with that hydrogen, this 2 goes with that hydrogen, and it doesn't go with this oxygen. Only goes with the thing that the atom that it comes after. Couple more for you before we quit. Let's look at magnesium and copper nitrate. We can take a chunk of nice shiny magnesium metal and put it in a solution of copper nitrate. Now copper nitrate, maybe at this point you can say to yourself, oh, that's an ionic compound. That must be a solid. Yes, indeed. But we can take that solid and we can dissolve it in water. And if we do that, then we'll have copper ions running around in there. And that's going to react with the magnesium. And we are going to end up with copper plus magnesium nitrate. So if you were given this equation, we should be able to balance it. Now think for just a second about what's going on here. This is kind of cool looking. So this would be a blue solution. This would be a nice shiny silvery colored metal. You know what copper looks like. So after the reaction, you're going to get that copper, which is the color of pennies, sitting on the bottom of the beaker. This stuff is going to go away. You won't see that anymore. And the blue color is going to go away. So where you have a blue solution in a nice shiny metal, you're going to end up with a clear solution and copper on the bottom. Very cool looking. So let's see what we can do to balance this. We have 1 magnesium, we have 1 copper, and we have, watch what I'm going to do here. I'm going to say that we have 2 nitrates. I have nitrates on this side and nitrates on that side, and there's no sense pulling this apart and looking at nitrogen and oxygen separately. It will only make it more confusing. If you have nitrate on both sides, just call it nitrate. Treat it as a unit and leave it alone. Now on this side, I've got 1 copper, 1 magnesium, 2 nitrates. Well, check that out. That matches. So as it turns out, that is already balanced. I don't need any coefficients for that, and I can just leave that alone. Let's change this though a little bit, and let's say that I'm going to use silver nitrate instead. And let's say that we're going to end up with silver precipitating out on the bottom. All right, that's going to change things a little bit, because look what happens here. You can see that on this side of the equation, silver has a +1 charge, nitrate has a -1 charge, so they're going to go together in a 1-to-1 ratio. Over here, magnesium has a +2 charge, nitrate has a -1 charge, so they're going to go together in a 1-to-2 ratio. Which means that in order to balance this, I am going to need some coefficients. So if you're ready to tackle this without keeping a spreadsheet down here, let's do it without that. Let's see what we've got. We've got 1 magnesium, 1 magnesium. Okay, so far so good. 1 silver and 1 silver. So far so good. But here's where we run into problems. 1 nitrate, 2 nitrates. So what we have to do over here is put a 2. So now I have 2 nitrates, and that's all balanced, but I have messed up my silver. Now I have 2 silvers. If I put a 2 there, now I have 2 silvers. So let's check the whole thing and make sure it worked. 1 magnesium, 1 magnesium. Again, even though we've got little subscripts over here, neither one of those belongs to magnesium. There's just 1 magnesium there. 2 silvers and 2 nitrates. 2 silvers and 2 nitrates. So we are balanced. Let me show you one more. And this is a combustion reaction. We're going to take C2H6. is known as ethane. And we're going to burn it. When you burn things, you react them with oxygen. And when a carbohydrate burns by reacting with oxygen, it always makes carbon dioxide and water. Well, I should say always. It always makes that as long as you have enough oxygen. And that's why it's really important that if you burn things, you do it in a well-ventilated area where there's plenty of oxygen. Because if you start running short on oxygen, instead of making carbon dioxide, it makes carbon monoxide. Carbon monoxide is very toxic because it starts grabbing onto your red blood cells, and it grabs your red blood cells way stronger than oxygen does. So pretty soon all your red blood cells, which are supposed to be taking oxygen to your body cells, including your brain, can't do their job anymore. And so your brain becomes deprived of oxygen, and in a few minutes you're dead. So make sure that if you burn anything, you do it in a very well ventilated area where there's plenty of oxygen. All right, back to business here. So we look at first carbon. When I do these, I like to just start at the beginning and work through. So 2 carbons, only 1 carbon. Let's just fix that right away. So now I have 2 carbons on both sides. 6 hydrogens, 2 hydrogens. We can fix that right away. Now I have 6 hydrogens. And now I'm going to run into trouble. 2 times 2 is 4 oxygens, plus 3 oxygens is 7 oxygens. So I need 7 on this side. And my problem is that this is O2. So I really need to have an even number of oxygen atoms. This has to be an even number over here, which means that has to be an even number over there. So the only way to get around this problem is just to double everything. So I'm going to start with 2 of these, which means that I'll need 4 of these and 6 of these. 4, 6. Okay, so 4 carbons, 2 times 6 is 12, 6 times 2 is 12. Now watch this, now the oxygens are going to work. 4 times 2 is 8, plus 6 is 14. So if I put a 7 over here, 7 times 2 is 14, and now it works. And that is balancing chemical equations.